All right, it is 45, so I think it's time to start. And hi, I'm Chris. I'll be hosting this track for the next few hours. And next up, we have Rúnar talking to us about multisets and Scala, I believe. And yeah, Rúnar has been an advocate of type functional programming for a long time. And I remember a bunch of years ago, you were standing on the stage at Scala Exchange. I think it was the keynote or something, and you were declaring passionately that you do type functional programming because it makes you feel good. You're also the author of what many just refer to as the Red Book, together with Paul. And I believe both of you, like more recently, for the more recent years, have been working on the Unison language, which personally I find one of the most interesting programming language projects out there at the moment that excites me. And yeah, today you're talking about multisets and Scala, so I'm handing over to you. Take it away. Oh, and questions we'll take after the talk in the separate Q&A room. All right, let's start.
Great. Thanks, Chris. Okay, yeah. My name is Rúnar. I'm going to be talking to you about multisets and Scala. Okay, so this is a data structure that is pretty useful, but for some reason it's not in the standard Scala library. So the purpose of this talk is really to tell you about multisets and to convince you that multisets are cool. And if there's anything that I want you to take away from this talk, is that multisets belong in your tool belt right along with lists, sets, and maps. So it's a really sort of basic data structure. So it's not just the Scala standard library that left out multisets. Ignoring multisets has a rich tradition. So for example, in the introduction to Smalltalk from way back in the year 2000, they say, well, applications of multisets are rare. So multisets were not in the standard Smalltalk library either. Okay, so, well, what's a multiset? So a multiset is like a set, except elements can appear multiple times. So it's also like a list, except there's no order to the elements. So there's no first element, and it has no head or tail or anything like that. Great. So another way of saying this is that whereas a set can be modeled as this characteristic function, so a function from A to Boolean, where that particular A is either in the set or it's not in the set, a multiset can be modeled as a function from A to the natural numbers. And I'm using here the type natural from the Spire library, which is awesome, by the way. So yeah, and that indicates how many times that A appears in the multiset. So 0 or more times. So these are natural numbers, including 0. Okay, so multisets are actually everywhere. Like for instance, your grocery list is not a list; it's a multiset. And like, what are the atoms in this molecule? That's a multiset, like H2O, there are 2 H's and 1 O. The prime factors of some numbers, the prime factors of numbers are multisets. For instance, like 3060 has the factor 2 twice and the factor 3 twice as well. So those are multisets that appear in mathematics. And also like the contents of your pockets are multisets. For instance, if you have $4.69 in your pocket, then you'll have $4 and maybe 2 quarters and like 4 pennies, etc. Shopping carts are multisets, super common use case in software. Database tables are multisets of rows, usually, and that's another super common use case. So anyway, why am I interested in multisets? Well, I read this paper, first of all, a really cool paper by Norman Wildberger, which is called A New Look at Multisets from back in 2003. This paper is very accessible, and it actually made me want to write a multiset library, which I first wrote in Haskell and then ported it to Scala. The other reason is dice. Now, we'll get to what dice have to do with multisets here in a bit, but first I want to talk about Dungeons and Dragons. So I love to play D&D. I used to play AD&D 2nd edition back in the early 1990s. You can give me a virtual high five if you used to play AD&D back in the day. Anyway, I picked up 5th edition of D&D in 2016, and I'm like totally hooked on this. So anyway, speaking of dice, D&D involves a lot of dice and probabilities. So if you're a total nerd like I am, and I think you are, you'll naturally want to do some statistical analysis on situations that come up in the game. So I'm usually the dungeon master for my games, and so I'm usually designing adventures and scenarios. And so I want to know things like, well, how many rounds can this monster survive an encounter with my players? Or how likely is it that this spell will kill the whole party? Stuff like that. And so in order to answer questions like that, I made this library that I just call Dice. And that's available on GitHub. And, I'm still working on it, but it's coming together. So you can construct dice using these sort of dice expressions. So for instance, a 6-sided die is represented by D6. So you just pass 6 to this function D, and that constructs dice, which is just a single roll of a 6-sided die. You can construct a roll of 8 6-sided dice, and that summing them all together with the expression 8d6. So that's another die roll. Constant 4 is a die that always rolls 4. You can add dice together. For instance, you can have a d6 and a d4 and then add the results. You can multiply results. So this is an 8-sided die that is multiplied by 2 if a coin flip comes up heads. You can divide dice by other dice or by numbers. So this is half of the result of 8 6-sided dice. I have this combinator reroll. So this is a 6-sided die rerolling the roll if it comes up 1, but keeping the reroll. And this is rolling 8 6-sided dice. So this repeat combinator. So you roll 8 6-sided dice and re-rolling any ones. It also has map and flat map. But so map, for instance, here I'm rolling a 20-sided die, and then if it comes up 1, I'm going to treat that as a 20. And then you can do crazy cool stuff like, well, D6, which is a number of 6-sided dice that is determined by a roll of another 6-sided die, or DD100, which is a die whose number of sides is determined by the roll of a 100-sided die. So the main thing that I want out of this library, the main thing that it gives me is a probability distribution for the dice expression. So it's not primarily about rolling dice. You can sample the probability distribution to actually roll the dice, but the main thing I want are these distributions. So for example, I can get the probabilities out of a d6, and it shows me that this is an even distribution where every element in the map comes up 1/6 of the time. So what does this have to do with multisets? Actually a lot, because the main workhorse of this dice library is the multiset. In fact, the dice library is doing nothing interesting. It's just delegating all of the work to the multiset library that I wrote. So that library is available on GitHub as well. I'm calling that MSet. It's Scala MSet on GitHub, in my GitHub. And the main feature of that is this multiset class. And the representation of the multiset is just a map from A to natural numbers. So it's 0 or more A's in the multiset. Okay, so for example, here's an example constructing a multiset. We can construct the multiset from like a sequence. So here I'm constructing one from the string abracadabra, and that gives us the multiset of the characters in the string. So this gives us an easy way to count elements in the input. So you can see there are 5 A's, 2 B's, etc. in the input. You might also notice that this is a probability distribution for the characters in the string. See, dice, right? So we'll get to that. So anyway, what can we do with a multiset? So this library supports a number of operations on the multisets. We can ask for the multiplicity of an element in the multiset. So this is how many times the element occurs in the collection. This is also called the occurrence of the element. For instance, there are 5 A's in the multiset constructed from the string abracadabra. Two multisets can be compared for equality, and they are equal if for any element x, the multiplicity of x is the same in both multisets. So in other words, if they contain all the same elements, a cute application of this is to check whether two strings are anagrams of each other. So for instance, coronavirus and carnivorous are anagrams. So there's an order on the multiset, so we can compare them. One multiset can be larger or smaller than another. This is the case. So if tapes is less than or equal to, or at most potatoes, because for any given element in the first multiset set, there are at most as many elements in the other one. So for instance, there are two T's in potatoes, and there's only one in tapes, and so therefore tapes is smaller. And it's not the case that for any of the elements, there are more of those elements in tapes. Like there are fewer of each element in tapes than potatoes. Anyway, you get it. So there's also multiset union, which is pretty different from set union, although it actually coincides with set union, but kind of a counterintuitive thing. So in the union of two multisets, given any of the two elements, there are like at most, or there's the max of that element in the union. So for example, there's one O in one of these things and two O's in the other one. So in the union of them, there are two O's, which is the max of how many O's there are in the inputs. All right. And then the intersection is the other way around, where we take the minimum of the counts in the two multisets. So in the intersection of sleeveless and senescence, there are two S's and four E's, because there are at least two S's and at least four E's in each of the inputs. And then there are zero of the others, because there are at least zero of the others. And then we can take the direct sum of two multisets, where we actually add the multiplicities for any given element. So for instance, here there are three O's in the output, because there's one O in one input and two O's in the other. All right, so this is more of what you might think of like as the union, but what's really happening is, with that intuition, is that the direct sum and the union for sets actually coincide. They are the same. So like the max of true and true is true, so which is also their sum. Okay, we can also take multiset difference. So the difference is where we just subtract one from the other. And I'm using here the sort of minus sign rather than the minus sign, which means that this is on the natural numbers. So like 1 minus 2 is 0, doesn't go negative. So we just subtract the number of for each element, subtract the number of times that element occurs in the second one from the first one. Okay. We can also take the direct product of two multisets. So then we get all the pairs in the multiset, where the number of times a given pair occurs in the result is the product of the number of times that each element in the pair appears in the inputs. For example, there are two PEs in the output here, because there's one P and two E's, and 1 times 2 is 2. Okay. So the operations on the multiset together form this really interesting algebraic structure called a realm. So this term realm is from the paper by Wildberger. So he calls this thing a realm. And it has these 4 operations. So sum and zero you might recognize from the monoid. But then there are these 2 additional operations, meet and join. And so, and those 2 form a lattice. So a realm is a lattice together with a monoid, so that they interact in an interesting way. And I'm going to talk about that here in a bit. Anyway, for multisets, the meet is their intersection, the join is their union, the sum is the direct sum, and then zero is the empty multiset. There's also a realm on the natural numbers, where meet is the min, that is, the lower of the two numbers. Join is the higher of the two numbers. Sum is their sum, and 0 is just 0. And then for Booleans, for example, meet is and, join is or, and then sum happens to also be or, and 0 is false. And so anyway, these operations, they have to obey a bunch of laws. So a realm, is a distributive lattice as well as a monoid, and these have to interact in a specific way, which is laid out by these laws. So multisets actually have a rich algebra. So they're pretty interesting objects to study. So anyway, we can generalize multisets. So, and I do this in the library, actually. We have generalized multisets. So we have this class mset MA, where M is the type of the multiplicities, and A is the type of the elements. And so that's just represented by a map from A to M, where the ordinary multiset is an M set with multiplicities in the naturals, and the ordinary set is an M set with multiplicities in the Booleans. And there are lots of there's like a whole zoo of these things. Like we can have negative occurrences. So where any given A can appear like -3 times or something. There are fractional occurrences. These are sometimes called fuzzy sets, where things can appear a fraction of a time in a multiset. And then there are these sort of inexact occurrences where, for instance, you might have in your shopping list, for instance, you might have like 2 to 4 onions or something. Like it doesn't have to be an exact number. Okay, so when that is an M set where the multiplicity is an interval. So here, if M is a realm, that is, it's a lattice with a monoid, then M set MA is also a realm, as long as there's an equality on the A's. Also, if M is a realm, then M set is a monad. So we get map and flat map. And so we can use these things in 4 comprehensions. Also, if M is enumerable, that is, if you can enumerate them from the beginning, like natural numbers, 0, 1, 2, 3, or the Booleans, false, true, then the M set is traversable and foldable, which is super useful. So that brings us back to dice. The generalized multiset I'm using in the dice library, where I have this type, which I'm calling just a distribution. And so a distribution of A is an M set of A's with multiplicities in the rationals, with a convention, and I can't actually enforce this in the types. The convention is that the multiplicities are positive rationals between 0 and 1. And so the sum of the size of the multiset is always either 0, or if it's empty, or it's 1 if it has any elements in it at all. And then my dice is actually just represented by a distribution on the integers. So great. So a die roll is just a probability distribution. And dice form a realm, which is cool. So we can absolutely have multisets whose elements occur a random number of times. So for instance, I might want to have a random encounter in Dungeons and Dragons as a multiset, where that multiset contains 1d4 hill giants, 1d6 ogres, and 2d6 bugbears, or something like that. And then I can actually traverse that multiset and generate, I can generate a probability distribution of like just how many of each of these things I'm gonna get in the end. Okay, an M set is really doing all of the work for the dice library. Like most of the operations on dice are just delegating to the operations on the M set. For example, flat map really just delegates to flat map on the M set. And then adding to die rolls is also just delegating to flat map on the M set. So I just say, to add 2 dice, I say, well, 4x comes from this dice, and y comes from the dice D. I yield x plus y. And that, we'll get all of the combinations and add them together and give me a distribution of the result. Okay, so here's an example use case for this. Like, an example of how I'm using the dice library. So Fireball is probably one of the most iconic spells in Dungeons and Dragons. So it's a big ball of fire that does damage to everyone in a specific area. And you'll note that there are 2 dice rolls involved here in the text. So one of them is called a saving throw, which allows a creature affected by the spell to avoid some of the damage. And the other one is the damage roll, which determines how much damage the spell actually does. And so the player who controls the creature affected by the spell rolls this 20-sided die, and they have to roll some number higher than something that's determined by the spellcaster's ability. And for a wizard that's high enough level to cast Fireball, that number is maybe 16 or so. And so on a 20-sided die, you have to roll at least 16. And the target then gets to add some bonus based on their level and their dexterity, which is, how quickly you can react. And then the wizard rolls 8 6-sided dice to determine the damage. And then if the target's saving throw succeeds, that damage is divided by 2 or halved, rounded down. So the kind of thing, the question I want to answer is like, well, what kind of damage can I expect to do with Fireball for any one creature? And like, what does the probability distribution look like? So we can just write that as an expression in the dice library. So a saving throw, given the target's bonus, the difficulty, which is determined by the wizard's level, some roll to do if the saving throw fails, and some roll to do if the saving throw succeeds. And I would just say, well, roll a d20 and add the bonus. And then if the roll is greater than or it meets the difficulty at least, then it's a success. Otherwise, we fail, right? And then we yield the damage. So, this is it looks pretty nice, I think, to write these expressions. And then Fireball just calls saving throw with the specifics. So, it takes the target's dexterity save bonus, it takes the caster's spell save difficulty class, and on a success, it halves the damage, so 8d6 divided by 2, and on a fail, it does the full damage, 8d6. And then I can get the probability distribution out using the probabilities method on the dice, and then we can plot that. For instance, using a library like Evil Plot, which is a pretty cool little library for plotting in Scala, we can show what this distribution looks like. Now, this graph was actually made in Mathematica because I actually didn't have time to make Evil Plot's output as nice as I would have liked it, but I could probably get it there. But anyway, this is a visualization of the output of the function from the previous slide. So looking at the histogram for this damage, we can see that this is a combination of 2 normal distributions, and like there's a narrow one centered around 14, which is in case the saving throw succeeds, and then there's a fat one in case the saving throw fails. And then the relative heights of these 2 humps are affected by the spellcasting ability and the caster of the caster and the dexterity of the target. And so the average given some particular combination of those numbers, I found out was like around 20 or something. Okay, and here's like another example that I did. This is the spell Steelwind Strike, which is like a 5th level spell. So it's vastly superior to Fireball, and it can do up to like 600 damage. But like the average is like around 100 or something, given the armor class of like a particular target or whatever. But it has this kind of interesting probability distribution, which is cool to see. And I can see like, okay, what's going to be my average, and like what are the spikes that I can expect, and I can plot the standard deviation here, which I do with the dotted lines, dashed lines. Another visualization I made using this was for the sleep spell. And so sleep is a spell that puts creatures to sleep based on their number of hit points. And it's really good at low levels, and I knew it was really good at low levels, but also knew it was really bad at high levels. So I wanted to know like what is the inflection point, like what's the sort of sweet spot. And from this visualization, I know it's hard to see on the slide, but from this visualization, I could see that around total 20 hit points, is the sweet spot for the targets. So, you know, you can put between 2 and 4 goblins to sleep reliably, or like a couple of wolves or a single orc, but not like an ogre or a troll or something. Like it stops, the where it goes red towards the bottom is where the probability of the spell doing nothing goes to 100%. And you know, so zooming in on this a little bit, you can see this. The sweet spot for 2 creatures like is 10 per creature. So you can reliably put a couple of creatures with 10 hit points each to sleep. Anyway, I mean, I thought that was cool to see using my little library. So you know, that's my little talk about multisets and my little dice library. And I think I actually have time for some questions if anybody has them.
Okay, so there was a question earlier in the Q&A section.
Sure.
From 1102, can you please explain negative occurrence? I'm not getting A occur 3 times negative. I don't know what slide that was, yeah.
So let's go back to that slide.
And the question was asked by Harmeet Singh.
Okay, yeah. So, so the negative occurrences are pretty abstract. So it's like you can have a multiset where you have like 3, I don't know, onions or whatever. Okay, and you want to say subtract stuff that you've already bought. Like say you have a shopping list with like 3 onions, and then you have stuff you've already bought, and you might want to subtract, a couple of onions or whatever. Like one way you could model that is like, okay, well, I'm just going to subtract one from the other and like go to 0. But if you want to model something like, like debt or something, like, oh, I bought too many onions, and so actually now have bought, or next time I go to the store, I need -2 onions or something. I don't know, but you want to model where you go negative, and so then it's not so this is a way of doing that. So if you have like a multiset with -3 onions and you add that to a multiset with a bunch of onions, then you'll decrease the number of onions in that multiset by 3. Sorry about the example, but I didn't have anything prepared for that. If you're interested in the mathematics of this, like there's a paper from 1987 called Negative Membership, and that shows that a theory of multisets with negative multiplicities is actually equal to ZFC set theory. So that's pretty interesting, that like using negative occurrences in the multisets, you can actually model set theory.
I just found a link to that paper and posted it in the chat.
Cool. Was there anything
else? I think we only had that one question so far. So maybe we'll wrap it up here. And as I understand, Rúnar, you will be available for questions in the separate Q&A room after this talk.
Absolutely.
Where attendees also can enable audio and ask questions more directly if they want to.
Cool.
So I'll post the link to that room also in the chat. And yeah, thank you very much for telling us about multisets and what you've been doing with all your time at home now.
Thank you.